Hi y'all, my name is Jack, and I am an organic chemistry tutor down in the Math and Science Center. And today I'm going to be going over saturated versus unsaturated compounds in terms of organic chemistry because this can be a little bit challenging for people to understand at times. So a saturated compound has the full amount of hydrogens available to be able to bond. Like this is a saturated compound. Saturation is can also be affected by the amount of nitrogens, halogens, and rings present as well. And saturated compounds usually don't have any double bonds or rings, and unsaturated compounds have double bonds or triple bonds or rings involved. And unsaturated compounds can have varying degrees of unsaturation. And here is the formula for the degrees of unsaturation. So for N, that's our typical symbol for nitrogen. X is the symbol for halogen. H is hydrogen. And C is carbon. So here we can see that this is a formula for the degrees of unsaturation. So we have 2 times the number of carbons plus 2 plus the number of hydrogens minus the number of halogens and minus the number of hydrogens divided by 2 gives us the degree of unsaturation. And compounds can be unsaturated by varying degrees. Something important to realize is that halogens and hydrogens attached to the molecule decrease that degree of unsaturation. So if you want to look at how many carbons a molecule should have, or how many hydrogens a hydrocarbon should have, because this is usually in regards to alkanes or alkenes, because an alkane is this sigma bond, and alkane has a pi bond, making it a double bond. So we're going to go over these two as a little example and to be able to calculate the degrees of unsaturation. So these are the same molecule, but this has a double bond. So we're going to use this formula, 2C plus 2, to see how many hydrogens we should have. So each of them have 4, so 2 times 4 plus 2 is equal to 10. So we should have 10 hydrogens. Here we have 4, and 2, so it does have 10. Here we have 1, 2, 3, 4, 5, 6, 7, 8. So we only have 8 hydrogens there. This is obviously not how many hydrogens we should be if we were fully saturated. So to be able to calculate that, we can kind of go back over here, but we kind of can ignore the nitrogen, halogen, because where there are no nitrogens or halogens in these molecules. So here we only have 8 hydrogens. So how I work this, and this is how I think of it pretty effectively. So we have 10 hydrogens minus 8 hydrogens is 2 hydrogens that we're missing. But this is where that division by 2 comes along. So 2 divided by 2 is 1, and that's our 1 degree of unsaturation in this molecule. So this molecule, again, is unsaturated by 1 degree only. If you could see if that there were more double bonds or even rings, like we had mentioned earlier, this could also increase the degrees of unsaturation. You can sometimes get the degrees of unsaturation, and you have to guess whether or not it's created by double bonds or rings, and that just goes into playing with drawings to see how you can make something to fulfill the requirements of unsaturation. Another important, more applicable side of this is in our fatty acids and fats that we consume on a daily basis. So you've probably heard of saturated fats or trans fats or unsaturated fats, and this is what this is all about. So saturated fats have no double bonds in their little fat in this fatty acid tail. This means that they pack tightly together, and when something is packed tightly together, it requires more energy to break it apart, which is why these saturated fats are often solid at room temperature, because they require greater thermal energy to disrupt this tight packing, which is why they're solid again at room temperature. Unsaturated fats come in two forms, which is in regards to the alkene, whether it is in a cis position or if it's in a trans position. Here we have some fats that are, well, here, let me write this down. Here's saturated. These are both unsaturated, but you could pause for a second, think about which one is trans and which one is cis. Well, this is cis. This is a cis double bond, and these are unable to pack tightly because those cis double bonds, as indicated here and here, form kinks. So the rest of the molecule goes off in this direction instead of packing tightly. So this is an unsaturated cis fatty acids. And then this is an unsaturated fatty acid, but the alkene is in a trans position. And that trans, this is where trans fats come from, because these double bonds are actually more favorable because, again, entropically, more bonds are more favorable. And so these require greater energy to break apart than it would be to just a single bond. So these trans fats are actually really kind of killing you, literally and figuratively, but saturated fats are able to pack in and have that double bond, making them very tightly packed and more resistant to breaking apart easier. So that's why that these are so bad for you, is because they pack in tightly and that alkene helps to stabilize them. These are the best kinds of fats for you. These are usually our oils, like olive oil and stuff like that. Trans fats can be found in like margarine and all that stuff that we try to avoid now. And yeah, so these unsaturated fats are what keep things liquid, which is keep like oils liquid, because that kink really disrupts the separation, disrupts the packing, which makes it easier to separate. And yeah, I hope that this was helpful. And if you need any help, you can always come visit us at the Math and Science Center.